Good afternoon, everyone. Good morning to those of you on the West Coast. I know that we have quite a few of you joining us from Saskatchewan, Canada, and California, and Arizona. So if you are out there, welcome to you as well. I'm Michelle Avila, and I'm going to be your moderator for today's webinar. We have a lot of you. We're expecting a lot of people today, so if you have any trouble hearing me, although I suppose if you can't hear me, you won't hear me saying this, but if you are having any trouble at all with anything, you can just enter in a question, and I see that some of you have already figured out how to do that because we do have some questions up there. And while the rest of you are sort of figuring out everything, how to get on and adjusting audio and everything, I'll just go through some quick slides about Hypertherm, and then I will hand things over to Jim Colt, who is here with me today at our facility in Lebanon, New Hampshire, is where we are located. And we will get going. It's a long webinar. Jim has a lot to go through, so we will try to cover as much as we can. So a little bit about Hypertherm. I assume that most of you do have Hypertherm equipment and know who we are, but Hypertherm was founded in 1968 in Hanover, New Hampshire, which is just 3 miles from where we're sitting here today. We still have our main facility located in Hanover. We have one or more than one in Lebanon, 12 facilities in all in this area. We are an associate-owned company with more than 1,400 associates around the world, and are proud to devote more engineering resources to cutting research and development than any other company out there or any other company making cutting equipment. We have about 120 cutting patents. You will actually hear about some of those patents today, and are working to continuously improve the cut quality, the productivity, the operating cost, and the reliability of our systems. So our products include plasma systems, which is really the subject of today's webinar. But in addition, we also make laser cutting systems, water jet cutting systems. Those are actually manufactured out in Minnesota. We have our automation products, so our CNCs and our torch height controls, software, both 2D CAD/CAM nesting software and 3D robotic software, as well as consumables for both Hypertherm and non-Hypertherm systems. And that takes us to Jim Colt. As you can see here, Jim Colt is an applications technology manager here at Hypertherm. He is employee number 11. Employee number 11. Actually, the second most senior person here at Hypertherm. I didn't want to say old, but the most senior person here at Hypertherm behind our founder.
Longest employee here, maybe.
Oh, longest employee. He is the longest employee in Hypertherm history because everyone else is retired.
Right.
All right, so there you go.
Okay, now one more thing, Michelle, while you're right here. We're doing the first part of this webinar today, which is on electrodes. And mainly because we have a whole presentation on consumables optimization that covers electrodes and all the rest of the components in the plasma torch. And in the past, we had to rush through the electrode section, which is the longest section, very rapidly, missing a lot of important points. So next week, I believe, we're going to do everything other than electrodes, right?
Yes, exactly 1 week from today. So we'll cover the shield, the nozzle, the swirl ring, the retaining cap, all of the other items that make up a typical consumable stack-up.
That sounds good. And once again, at the end of this, we're going to have, we'd like you to type your questions in as we go, and we're going to try to address as many of the questions as we can at the end of my talking part. And whatever we don't address there, we will get back to everybody via email, right?
Correct, yep.
Okay, well, let's get on with it. Okay, so we're talking primarily today about mechanized plasma cutting, but what we talk about with all of the consumables really kind of goes across the line with all plasma torches, whether it's an air plasma torch or one of our high definition class plasma torches, and even with other brands of plasma cutting torches. They all act a little bit differently, but there's some similarities. And as an example, the electrode serves the same function in every plasma torch in the world. It's still does a lot of the same things. We like to point out a lot of the patented features that we have while we're talking about it, that do enhance either cut quality or consumable life or both. So we'll do that as we go through this. So with today's long life oxygen cutting technology, plasma is the most productive, cost-effective way to cut carbon steel from gauge to 2-inch thickness. Of course, we can cut all of the other conductive metals out there, primarily stainless steel, aluminum, copper, brass, things like that. But I'd say probably 90 to 95% of the users of plasma spend most of their time on carbon steel, so we spend most of our time talking about that as well. I want to apologize a little bit in advance, suffering a little bit of a head cold up here, so I will occasionally clear my throat just so that I can keep on talking, and hopefully my voice will hold up, or Michelle, you'll have to take over for the end of this. But anyway, to get to the highest performance level, operators of any plasma cutting system, whether it's handheld or mechanized cutting, need to ensure that the consumables in the torch get inspected regularly and are maintained to high standards. They're really the key to getting the energy density out of the torch and the cut quality that you need. So we're going to be spending a lot of time talking about this little part, but it's really the starting point for the plasma arc, the electrode inside the plasma torch. Looks like a fairly simple part, and it does look like a fairly simple part. However, you've got to remember that the arc that comes off the emitter on the end of this electrode, the hafnium emitter, the little shiny silver point you can see in this picture, the arc at that point is over 3,000 degrees Fahrenheit, and then the arc gets squeezed further down the channel through the nozzle orifice and can be as high as 50,000 degrees Fahrenheit. So there's some very high temperature physics that go on inside this torch. Copper, as an example, melts at 1,100 degrees, and we've got 3,000 degrees right on the end of the electrode. Why does it last as long as it does? Well, hopefully after we get through this presentation, we'll all understand a little bit more about it. And even after 38 years working, with plasma cutting day in and day out, it still amazes me that you can get more than a mile of cutting out of one of these electrodes at the high temperatures that are going on inside there. So we're going to talk about the function of the electrode, the critical features of an electrode, what can go wrong, measuring wear, and how to get the best life out of electrodes. If you can make your electrodes last longer, all the rest of the parts in the torch will work better as well. So the primary function of the electrode in any plasma cutting torch is to provide the actual power to the plasma arc. The electrode is actually connected to the negative output from the power supply. There's a bunch of other functions that the electrode does as well. We're going to talk about each one of them. So if you're running a 400 amp torch, the 400 amps passes through this electrode. It actually starts the arc on the hafnium emitter on the end. So let's talk about other functions of it, and then we'll get into a little bit more detail about what it does. The secondary function of an electrode is it conducts either high voltage, such as high frequency that we hear about for starting some plasma torches, energy during the starting sequence. So that creates an arc actually between the electrode and the nozzle in the front end of the torch. Absolutely critical to fire the plasma torch. Now, there's a couple of different ways to ionize the gas in the plasma torch. One is with high frequency or high voltage, kind of like the little spark that occurs on your lawnmower engine spark plug or your automobile engine spark plug. We actually pass the cutting gas through that spark. That spark actually increases the energy that's stored in the cutting gas and eventually reaches ionization temperature, and that makes the gas more electrically conductive and allows the plasma arc to start. So we'll see, I think in the next slide or in the next couple of slides, we'll see a slide of just kind of how that works. Since the electrode is the main contact for a plasma arc, obviously it gets very hot. The end emitter on an oxygen electrode is made of the element hafnium, and it can reach temperatures exceeding 3,000 degrees Fahrenheit, and that's actually the melting point of hafnium as well. Most plasma cutting electrodes that are used at over 125 amps of cutting current are liquid cooled. We do make air plasma cutting systems up to 125 amps that actually use the same air that's doing the cutting process to cool the consumables in the torch. But once again, over 125 amps, everything that we produce is liquid cooled, which gives you an advantage on the cooling. Okay, so just this slide right here, the upper left side is a typical high-frequency start plasma torch. It's kind of just a simple schematic of the torch that shows the two important parts, the electrode and the nozzle in the torch, and of course the workpiece, which is the piece of metal that we're going to cut. To get one of these torches to fire, we actually swirl some gas around the electrode. On most liquid-cooled torches, we're using either oxygen or nitrogen or a variety of other gases on an industrial application. But what we need to do with that gas is to swirl it around the electrode. And next week, when we talk about swirl rings, we'll tell you exactly why we swirl the gas in the plasma torch. Swirl it around the electrode. It passes out through the orifice on the front end of the nozzle. Just cool gas, could be oxygen or air coming out. And what we do is actually establish a high frequency, about a 15,000 volt at very high frequency AC arc between the electrode and the nozzle. So this gas is actually forced to pass through that sparking that's going on in the front end of the torch. And that spark adds energy to the gas, increases its temperature until it reaches ionization temperature. And then you can kind of think of the gas coming out the front of the torch as the wire in a wire feed MIG welder. It's actually bringing the current down to the plate, and the force of the gas blows it away. And we add DC energy to that arc. That makes it that much hotter. And once we get the arc started, it's self-sustaining, and we don't need the high frequency anymore. About 20 years ago, Hypertherm invented something called blowback technology, and we invented it to make a simpler starting circuit to allow us to make our handheld plasma cutting systems, especially our air plasma cutting systems, more portable so that they could be used in the field a lot more. We needed to get rid of that high frequency starting circuit. And so we developed a process where the electrode, if you can see the bottom picture here, the electrode actually slides inside the nozzle. Oops, sorry about that. So the electrode slides inside the nozzle on the torch, and before you fire the torch, the electrode is actually touching the nozzle. They're dead shorted. The nozzle's at positive power supply potential, the electrode's at negative. And as soon as the air reaches the torch, the air blows the electrode away from the nozzle. That's why we call it blowback. And when the nozzle and electrode lose their electrical connection, it creates a high-intensity spark, much like the high frequency that we do in the upper picture. That spark is what ionizes the gas, and that's what fires up the Hypertherm PowerMax line of air plasma torches. No high frequency. There's advantages and disadvantages to each. We keep the high frequency starting process on our high-end industrial systems because it's a very reliable starting method, and it allows us to build the torches with much better, tighter tolerances to control the edge angularity much better in mechanized cutting applications. Where the sliding electrode that's used in our PowerMax torch, the advantage of that is less circuitry in the power supply. The power supply is lower cost and less complex as compared to the larger systems. And another advantage with the PowerMax is when you put them on a low-cost CNC cutting machine, they don't have that high-frequency arc that can affect sensitive electronics. So there's advantages, disadvantages, but for right now, the blowback start stays on the air plasma cutting systems, and high-frequency start stays on the high-end industrial systems. So the electrode acts as a starting point for the plasma arc. The copper body of it, you can think of it as a heat sink to make the hafnium emitter last longer. We'll see what the hafnium emitter is here in a few minutes. Generally, industrial or liquid-cooled plasma cutters use a high-frequency discharge, and air plasma systems, at least the modern ones made by Hypertherm and a few other companies today, use blowback starting technology. So let's look at the electrode and talk about the critical features of the electrode. And these pictures, for the most part in this presentation, are pictures of our high-definition consumables, liquid-cooled torch, like you would use on an HPR, an HPR 260 XD, HPR 130 XD, HPR 400 XD, and an HPR 800 XD that we use, that Hypertherm produces. So the center part of the electrode is the single most important part of the electrode, and that's called the hafnium emitter. That's because hafnium is something that emits electrons very efficiently, and there are a few other earth elements that will work, but hafnium works the best. We don't use it because it's cheaper, we use it because it's the best process. You'll notice on Hypertherm electrodes that the hafnium emitter is much smaller in diameter than many other brands of electrodes, including so-called copies that come from aftermarket suppliers in the industry. What we do is we actually size the hafnium emitter depending on the size, on the amperage rating of the electrode. And by doing that, we're able to transfer the heat out of the hafnium into the copper and then back into the liquid cooling system much more efficiently. So we're not putting a smaller piece of hafnium in our electrodes just to save money on hafnium. We're putting it in there to make the electrodes last longer. Okay, we'll talk a little bit about life here in a few minutes as well. Hafnium is a poor thermal conductor. It's bonded to the copper body of the electrode using a proprietary process that ensures excellent thermal and electrical connection between the copper and the hafnium emitters. Hypertherm electrodes do use a patented process, as I mentioned, that matches the diameter of the hafnium to the power level. So there is a different electrode for 30 amp cutting as compared to the electrode used for 130 amp cutting or 260 or 400. You'll see the hafnium size gets a little bit different. So I guess the point I'm making there, don't swap electrodes. If you're running at 400 amps this morning and want to switch to 130 amps, you need to use a 130 amp electrode. We'll spend a little bit of time talking about that as well. Dimensional stability is very important to ensure cut quality. Make sure that it's repeatable and that the electrode fits well with the other internal torch components. I'm actually, the conference room we're talking from right now overlooks the machine shop where the electrodes, nozzles, and other things are made. And if you ever do get a chance to come to New Hampshire, we'd be happy to give you a tour of it. Very high-tech automatic machines. They're running multiple shifts a day, manufacturing these consumables and holding extremely tight tolerances. So incorrect length or diameter will affect alignment and, in fact, cut quality as well as consumable parts life. So here's an electrode that, on the left side of the picture, you can see I actually sliced it in half with a bandsaw so we could see what's inside, and I put a little piece of paper in there just so we can see some of the features. So internal to the electrode is a very accurately machined bore and step, and that's up in the back end of the electrode. We'll see what that does in a picture in a few minutes, but what it actually, the description is that it ensures superior cooling as a result of perfect alignment of the coolant tube that we'll see in the subsequent picture to the hollow milled post on the bottom. The post on the bottom actually contains the electrode emitter, the hafnium slug. It's almost like a little piece of hafnium wire that's inside that hollow milled post. It's actually swaged in there. It's very, very well manufactured for good conductivity, both electrical and thermal conductivity. The alignment of the cooling tube provides for very concentric coolant flow and cools the hafnium emitter much more efficiently. A couple of other things that are very important is the location of the shoulder on the bottom of the electrode. When this is screwed into the torch and then you stack the other consumables in on top of it, the stack-up tolerance is very critical. The dimension between the end of the electrode and the inside bore of the nozzle, absolutely critical to get repeatable cutting quality and so forth out of these consumables. And then last but not least, when you've got used consumables that you take out of the torch, and you stick them on the workbench and you want to know if you want to use them again, we'll know more about that after the end of this presentation because we're going to show you how to evaluate the electrode. But being able to look at it and determine whether it's a 260 amp or 400 amp electrode is very critical. So the part numbers, even a manufacturing batch number is marked on every one of these electrodes for identification purposes, and that is pretty critical. I do find as I get older that I think the people on the shop floor are making these numbers a little smaller on there, so you might need a jeweler's eye loupe to read them after a period of time out on the shop floor. So etched part number, that's what we use a laser for here, is to mark our plasma cutting electrodes. And the threads and locating shoulder are designed to ensure perfect concentricity. So this is showing that same cutaway electrode in the center picture here with the coolant tube, which is actually an integral part of the torch. And I've pulled the coolant tube out of the torch in this case, and you can kind of see there's a section or a step on the coolant tube that the electrode actually bottoms out on. The coolant tube actually floats in the torch. It's just held in by the O-ring that you see up on the top, the reddish colored O-ring. And as you screw the electrode in, that center section allows the coolant tube to wobble back and forth. When the water flow turns on, the coolant flow goes down through the center of the coolant tube, and it needs to concentrically come out of the end. You'll notice that way down at the bottom where it's labeled high velocity coolant, that 185 psi water flow goes in and concentrically, evenly, 360 degrees around, pushes the cooling tube to the center and makes sure that little hollow milled post that's in the end of the electrode is cooled very, very efficiently. Think about 3,000 degrees on the end of that, and we're pumping water at 185 psi in through a very slight orifice there. What that does, it increases the velocity of the water flow down there, which strips away the steam layer that builds up on the inside of the electrode and more efficiently cools the electrode. This is actually a patented process, this type of mount for the cooling tube and the way it works in the electrode, and it's proven to dramatically increase electrode life. So the key feature of both the electrode and the torch is a floating cooling tube. The tube is loosely installed in the torch, as I mentioned. Okay. Coolant enters the top of the tube at relatively high pressure for water, forced through a tight fit around the hollow mill of the electrode, and that squeeze increases the coolant velocity, effectively causing the coolant to strip away steam. All right. So critical features of the electrode, we've seen a few of them. That's most of them. There are a few other things. The material that the electrode is manufactured out of, it looks like plain old copper. It actually is a special blend of copper, and unfortunately this blend of copper is difficult to machine, especially the hollow milled post down in the end. It'll break tooling on automatic machines and so forth, but we insist on using it because it makes for a better thermal and chemical bond between the hafnium emitter and the copper electrode. If you buy these electrodes from aftermarket suppliers, I guarantee they're not made out of the same material that ours is. So, and we won't talk about the exact blend that we use.
Yeah, and the tolerance level's 8 times narrower than a human hair is what I...
Yes, absolutely. Yep, and especially the concentricity between the stack-up tolerance of the parts is what's very critical. We call it total indicator reading concentricity on these parts. So what can go wrong with the electrode? The most common thing that we run into is the operator putting the wrong parts in the torch. We'll take a look at a cut chart here on one of the next slides just to kind of show you what the operator has to look at. But if you put a 130 amp electrode in with a 260 amp nozzle, we've lost some of that concentricity because there are differences in dimensions from one part to the next. One can argue that we have a lot of different consumables choices that go in our plasma torches. But the reason for that is by fine-tuning each different power level with our torch, we can give you much better and more consistent cut quality. And so we're going to kind of stick with the way we do things as far as that goes. The most common issue with poor performance in terms of cut quality, cut speed, and the life of the plasma cutting electrode is using the wrong mix of parts. Okay, so we'll just take a quick look. I posted, this is right out of the operator's manual for an HPR 400 or an HPR 260. This is showing the actual consumables and their part numbers and the way they fit in the torch in order. Way on the left is 220-637 is the outer retaining cap. Next is the 764 nozzle. Next is the 760 inner retaining cap. I'm sorry, the 764 is a shield, then the inner retaining cap, and then the 439 nozzle, then the swirl ring, electrode, and the cooling tube. These have to work together. If you don't have, if you have that doubt, make sure you look at that laser etched part number on every one of these parts. Make sure you've got the right stack up in the torch. That makes a big difference. Cut chart shows correct consumables to use for the range of all thicknesses and power levels. All the parameters in these cut charts, too, I'll just mention, are developed in Hypertherm's process development labs for best cut quality and consumable life. I suggest every time you do a cutting process, stick with these parameters. The only ones that you ever want to change here, you might want to play a little bit with cut speed. If you're getting a little bit of dross, go faster. If you're getting a little bit of edge bevel, go a little slower. But don't mess with gas flows, pressures, or amperage because that will affect the consumable parts life as well as cut quality. And that's something that's very well engineered on the Hypertherm torches. Use only parts suggested by the operator's manual. I can't overstress that. Okay. What else can go wrong with an electrode? What can cause an electrode to wear? Gas delivery system leaks or restrictions quite often can do it. Even a minor leak in an HPR XD gas system, it could be the inlet plumbing or hoses, excuse me, or it could be a regulator with a leak, it could be a split hose, a lot of those things. Oftentimes the flow rate on the inlet plumbing is high enough so if you have a little leak at a threaded fitting or something like that, it could suck in air when you should be cutting with absolutely pure oxygen. That usually affects electrode wear dramatically. And when the electrode wears out faster, so do the rest of the parts in the front end of the torch, and we'll see an example of that here in a few minutes. Okay. When you're talking about air plasma cutting systems, when it's supplied from a local compressor, make sure that the air is clean, dry, and oil-free. So you if you have a compressor that's such as a rotary type compressor that's going to spit a little bit of oil into the air, you need oil separation. If you've live in a real humid environment, you probably need some sort of a air dryer on the outside, on the outlet of the compressor, such as a refrigerated air dryer, desiccant air dryer, something along that line, just to make sure that the air going through the system is clean. You can always, if you ever have questions about that, feel free to contact Hypertherm Tech Service. Send an email to me. I'd be more than happy to steer you in the right direction as far as that goes. What else can go wrong with the electrode? Electrode and other consumables in the torch should always be handled with relatively clean hands. That's a tall order to ask of someone that has to be working with steel all day long. You're going to have dirty hands, but keeping a supply of clean rags at the operator station is a good idea. Wipe your hands off a little bit before you handle the consumables, because the dirt or the grease, when installed in the plasma torch, can cause stray electrical tracking, especially during the high frequency starting of the torch. Last but not least, do not over-tighten the electrode. It has an O-ring seal. I always joke, and it's not really a joke. I actually saw a guy one time with a half-inch drive ratchet with a little 7/16 socket on, driving the copper electrode into the torch. You really should just use a screwdriver type or nut driver to drive the electrode into the torch, and just until you feel it bottom out. Don't try to reef it down. And the reason for that is it's made of copper, which is relatively soft, which can crush, and that affects the stack-up tolerance of all the consumables in the plasma torch. The other thing that can affect the electrode life is the coolant tube that we talked about a little bit earlier. Inspect the end of the coolant tube, especially if a catastrophic electrode failure took place. What's a catastrophic electrode failure? That's when you're standing too far away from the control and we get to the end of the life of an electrode. And we'll see more about that here in a few minutes. And if you're an operator of one of these machines and you've seen green flame come out at the end of a plasma torch, and if you have a liquid-cooled torch, shortly after that you'll see water come spraying out the end. That's a catastrophic failure. You use the electrode too long. And a lot of times when that happens, it can nick or burn the edge of the cooling tube. And if the cooling tube doesn't have a perfectly concentric end where it meets down on the inside of the electrode, the water coolant is not going to be concentric 360 degrees around the hafnium emitter, and you're going to have short life on the electrode. So if damaged, replace the tube. You should keep these in stock. I think when you get a consumable parts kit for one of our liquid-cooled torches, you do have spares in there. But keep in mind that they're there. There also are a couple of different cooling tubes. If you're using beveling consumables, for instance, in an HPR system, which are longer than the standard flat plate cutting consumables or eye cutting consumables, you do have to use a different cooling tube. So make sure the right one is in there. It's covered on the cut charts in the manual. Okay, measuring wear. That's what we really want to find out. How can we be sure it's time to change or not change the electrode in the plasma torch? So let's kind of take a look at that. And one of the reasons I always like to explain that, and I think we have plenty of time, the reason I put this presentation together was for an actual customer on the west coast of the U.S. that had 7 or 8 different locations, and they were complaining that the consumable life on their Hypertherm systems wasn't what they expected it to be, and it was affecting the cost of cutting parts. So I walked out on the shop floor after hearing that from the management team, and stuck my hand in the bucket, the 5-gallon plastic bucket that seems to be by every operator station at a mechanized plasma cutting machine, and grabbed a bunch of parts. We went back in the office and we laid them on the table. I had 3 or 4 electrodes, 3 or 4 nozzles, some swirl rings, some other parts. And we looked at them, and more than 40% of the parts that I had there could go right back in the plasma torch and would cut just fine. I knew how to inspect them. They didn't. So we identified a problem that the operators really didn't, when the torch started misfiring or the cut quality wasn't good, they really weren't sure what to change, so they changed all the parts in the torch. So this presentation will certainly help you with that, especially if you come back next week and listen to the remainder of it with the rest of the parts. The electrode is probably the most important one. So we're going to learn about measuring wear. We've already learned about what can go wrong, the critical features on the electrode. We know what the electrode does in the torch. So how do we measure it? How do we determine what's bad? So normal wear is observed by looking at the hafnium emitter. So this picture shows a new electrode on the left and a used electrode on the right. The new electrode already has a dimple in that hafnium. We learned that a number of years ago at Hypertherm when we first came out with oxygen plasma cutting, we used to make the front of the electrode flat. And we used to find when we'd go in the lab and measure cut quality, we'd find that the arc tended to wander a little bit, and until it got a certain number of starts on it, maybe 50 starts or 20 starts. And what was happening is the actual arc was creating a dimple in the front of the electrode, and it made the arc attach dead center without wandering around a little bit better. So we started machining that dimple in the parts so that they would start out of the box with good cut quality before having to wait 30 or 40 starts. So I always like to explain why that's there. And it's important because when we're measuring a used electrode, we have to compare it to the dimple in the electrode, not from the flat face on the front end of the electrode. Okay. So the partially used electrode on the right has a pit depth that is 23 thousandths deeper than the new one, and we'll see how to measure that in a little while. The pit in the front of the electrode is due to evaporation of the hafnium during starting and steady state cutting. On a good running system, that pit's going to be right dead center. It's going to look almost like a drilled hole in the front of the electrode. If you see it burning off to the side, we'll talk a little bit about that, and that's going to be a problem. So quite a few factors can affect electrode life, as we know. This particular electrode is being used in laboratory life evaluation. I actually grabbed this out of one of our electrode life test labs. This electrode on the right is cut continuously for 15 minutes, and then it stops, re-pierces, and cuts again for 15 minutes. Currently, there are 34 of these 15-minute cycles on the electrode shown here, which equals 8.5 hours of arc-on time and about 6,800 linear feet of half-inch steel cut. Right off the top of my head, that sounds like more than a mile. A mile's 5,280 feet, so 1.3 miles, 1.2 miles, something like that. That's a lot of cutting. And this electrode, from my judgment, the way I've looked at them all and the way I'm going to teach you to look at them, is approximately half consumed. That means we could get 2.5 miles out of this one electrode, cutting at 260 amps with one of our HPR systems. It's pretty amazing. And if you told me that 20 years ago, I would have said, no, you'd probably get a couple hundred feet of cut. We've really improved the life of the consumables over the years. So standard oxygen electrode, as used with our HPR systems, should be changed when the pit depth reaches around 40 thousandths of an inch. The main reason for changing when the pit reaches this depth is right at about 40 to 45 thousandths, cut quality changes take place. We start to see some more dross on the bottom of the cut and more edge angularity. And somewhere between 45 thousandths and 50 thousandths pit depth, that catastrophic failure will occur. That's when the green flame and the water will spray out the end of the torch. This failure will damage the nozzle, shield, and possibly the coolant tube. So if you look at the picture on this slide, you'll see the shield, the nozzle, and the electrode has gone through catastrophic failure. If I had changed that electrode a couple of pierces before that occurred, the nozzle and the shield could go right back in the torch, and you can continue cutting. The nozzle's more expensive than the electrode, so you've just cost almost 3 times the price of an electrode just by trying to get a couple more cuts out of it. So we're hoping that people will spend a little bit more time looking at the electrode. We don't want it to be changed too soon, but you've got to learn to change it before it fails completely. Sometime in the future, excuse me, I suspect that we may have some sort of a fuel gauge on a plasma cutting system that'll say, you've got 10 more cuts, buddy, and you've got to change your electrode. If you wait any longer than that, you're going to be buying a new nozzle and a shield. We're not at that point now. The technology to do that just hasn't been developed. We're working hard on it. We'll get there eventually, I think. So this set was used in a test until catastrophic failure. When the pit depth gets too deep, heat transfer properties fail, and the electrode melts rapidly. The green flame is copper actually burning instead of the arc burning off the hafnium. The nozzle and shield could have been reused, now are destroyed. If the arc doesn't hit stop, the electrode could melt the end of the cooling tube as well.
Okay, and Jim, I'm going to start just so
Sure.
that you catch your breath. There is a question that really applies to what we're talking about right now.
Yep.
Just to clarify, when you're talking about that 40,000, that pit depth, it's from the original pit depth, right?
That's correct. Yep.
Not the face of the entire electrode.
Yep, absolutely correct.
Okay.
In fact, we'll show a graphic of that just here in a couple of minutes. So it's you measure. We'll show a dial indicator measuring the pit depth and then measuring the additional wear on the same part number electrode. So this actual set of consumables, just for information, had over 5 arc hours on it. It was doing a 20-second cut duration test at 260 amps. So it would cut for 20 seconds off, re-pierce the material, 20 seconds, and this was on half-inch steel. This went through 914 of those 20-second cuts. That's 5 arc hours in over 4,000 linear feet. So you'll see as the cut duration gets a little slower and you have more starts on a set of consumables, you're probably going to cut a little bit less footage, but you get a lot of starts out of it. So there's a couple of variables that affect consumable life. So cutting machine operators generally learn to notice a change in cut quality or a change in the sound from a plasma cutting system, indicating there's something wrong with the consumables. And I can't hear it because I don't run a machine every day, but oftentimes I'll be standing there with an operator on a shop floor, and he'll actually run to the machine controller, and I'll say, why did you run to the machine controller? And they say, well, didn't you hear that noise? I think the electrode's about to fail in torch number 2. It's amazing how the operators can pick up on that after a period of time. But, so some operators will change just one consumable part. Maybe all you need to change is the electrode. Some will change them all and throw the rest of them in that 5-gallon plastic pail. Many plasma operators are under pressure by the boss, maybe, to get the longest life out of the consumable parts. I've heard many production foremen say, use the consumables until they fail. That way we'll get the most life out of them. And that's not generally true. So in most cases, changing the electrode before it fails allows the nozzle and shield to last longer, and it'll lower the operating cost while maintaining high cut quality levels. Always have to mention this too. There are a lot of, especially imported non-genuine Hypertherm parts that make it here into the States. Some of them even are coming today in packages that are copies of Hypertherm packaging. So be very careful where you buy your consumables. Make sure they're coming from a genuine supplier. They're not made the same. They can cause damage to the plasma cutting torch, and you won't get the same consumable. If you save a little bit of money buying them, but if you figure out the actual cost per foot of cut, it won't be the same. So let's look at actually measuring the electrode wear, and best way to cut your costs without sacrificing quality is to fully utilize the parts as much as you can. That means changing the electrode before it fails. That gives you more life on the rest of the parts. So learning how to gauge the electrode wear will determine the most effective time to change the electrode. This little device is called an electrode pit depth gauge. You can buy it from Hypertherm, or you can use a kind of an off-the-shelf from a machine tool supplier stand with a dial indicator gauge to measure the pit depth on the end. The way you do it, take an electrode with the exact same part number that's laser etched on it as the electrode that you want to measure. And what you do is you set your dial indicator gauge to 0 in the center of that little pit depth on the brand new electrode. The electrodes with different part numbers will appear similar but might have a different overall length, so make sure you're using the same part number electrode to do this. Okay. Next, so this shows the brand new electrode on the left, and I set the dial indicator gauge to 0. And then I inserted into that same gauge the used electrode that we've been taking a look at. And you can kind of see, I kind of had the gauge set up backwards, but it went back to 90, back to 80, and then 3 more thousandths past that. So the needle on that went to the left, or counterclockwise, and it went back 23 thousandths. So that's the actual wear on that electrode. I know it can go to 40 thousandths. You could push it to 45. So this electrode is roughly half worn out. Okay, very easy way to check it. The electrode is the only part on the plasma torch that you can measure like this. The rest of the consumables are kind of a subjective measurement. You've got to look at it with your eye and make a judgment on it. The electrode can actually be measured, and it's very important to do that. Typically on one of our air plasma cutting systems, if you have a PowerMax system, that wear rate is going to be different. It is covered in the operator's manual, and it varies from torch to torch. Some of them can go 1/16 of an inch. Air-cooled electrode can't go quite as deep as a liquid-cooled electrode. So you've got to watch that very carefully. A couple of rules of thumb: if you check an electrode after it's only been used for a few minutes, the first 10% of its life, it's going to wear rapidly. Then it kind of takes a set. It slows down. You can measure it after a couple of hours of cutting, and you'll say, hey, boy, it wore out real quick at first, and towards the middle of the cut, it stopped wearing out. And then it starts to wear rapidly again towards the end of that life. And that's because the heat doesn't transfer quite as effectively to the copper from the hafnium in the emitter in the center. In the middle of life, electrode wear is slow and predictable. So, end of life, right around 40 thousandths for liquid-cooled electrodes on Hypertherm torches.
And I'm going to interrupt again,
Yep.
Jim, because we just had a question about this. We have to point out that we do have the silver plus electrodes with the silver tip, and those can go to .80.
Those can, yeah, the silver electrodes, they're longer life electrodes. They cost a little bit more, but effectively they cost a lot less to run. They can go to, if you follow the directions in your manual, you can go to 80,000 square on a silver electrode. You do have to make some adjustments in your height control. When you go that deep, it causes the torch to run a little closer to the plate, and so you might have to dial up the arc voltage, unless you have a sampling type height control that will automatically compensate for those electrodes. But good point. I'm glad you brought that up, and probably should add that to this presentation. I've kind of forgotten about that. Okay, when you're looking at a used electrode, very common to have a little bit of a black swirl off the center. That's usually caused by coolant or dirt that was on the operator's hands. It really doesn't affect the operation of it. If they're very prominent, or if the whole end of the electrode body are discolored, you might have a problem with the cooling tube or the coolant inside the plasma system that's not working correctly. So the copper body should remain clean and shiny, even near the end of life of these electrodes, with the exception of a few swirl marks. Okay. Also, as I mentioned earlier, when inspecting a used electrode, carefully view the relation of the pit in the hafnium. It really should be perfectly centered on the electrode. It shouldn't be leaning off to one side or touching the copper. It should always be fully in the hafnium insert that's in the center of the electrode. And always inspect the integrity of the O-ring. If you see water dripping out the end of your torch, there's something wrong, and usually it's an O-ring that's damaged or even missing in some cases. All right? So how to get the best life? Ramp down errors. This is something that a lot of people don't understand. Many of our systems, all of our oxygen liquid-cooled plasma systems use some special technology that does a ramp down at the end of the cut, every cut cycle. It's totally, you know, the operator doesn't even know it's doing it. When the torch shuts down, it ramps down the current, ramps down the gas flow, and that's to re-solidify that hafnium element on the end of the electrode that's molten during the cutting process. For successful ramp downs, though, the plasma arc must remain attached to the workpiece. So think about it. If you're cutting a bunch of small holes, and the programmer has programmed a lead out that goes back into the center of the hole, and so the arc cuts 360 degrees around and drives back into the center, and the center slug of the arc drops down into the down into the cutting table. Expect that the plasma arc is just going to snap off. It's not going to get to do its controlled ramp down. It takes as much as 100 milliseconds, about a tenth of a second, to do. You actually can hear the arc, if you listen carefully till you hear it snap off, as opposed to shutting the arc off when there's metal underneath it. You'll hear kind of a soft shut off. That's very critical to do. So what I say, if you're doing a hole intensive part, make sure that your programmer uses what's called an afterburn. In other words, instead of a lead out that goes back into the center of the hole, the lead out should stay right on the radius of the hole, maybe a little bit past the lead in kerf. That allows the arc to do its ramp down. It actually also serves a nice function to smooth out the end of the hole. You don't get that little divot that's quite as pronounced on the end of the hole. If you're doing something like cutting strips out of a plate and having to drive off the end of the plate, it's a good idea to put a sacrificial plate, a piece of scrap metal off the end of the plate, and let the torch drive onto the scrap metal so it can do its ramp down on the scrap metal. If you just drive off the end of the plate and let the arc snap off, that's also not good for electrode life, causes it to wear pretty dramatically faster. This is true as well for air plasma torches. Even if they don't have that ramp down technology, it's tougher for the plasma torch to snap off the end of the plate than it is to shut it off with metal still underneath the torch. Okay. It's acceptable actually to have maybe 10% of your starts have ramp down errors. That won't hurt anything, but if you're doing hole intensive parts, make sure that you've designed the lead in or the lead out to stop the torch with metal underneath it. It's always the best way to do it. Always use electrodes with the correct amperage and gas settings. As we said earlier, increasing or using different gas settings will affect electrode life. Use the gas settings that the operator's cut charts suggest, and use the electrode in the correct combination with other consumables. That's pretty much the end of the electrode part. In the past, we used to do the electrode and all the other consumables, and we tried to fit it into an hour, and it was just too busy, so we split it up a little bit, and we're open. I think looks like we might have some questions.
We do. We have lots of questions up there. Yes, in fact, let me get to one of our first questions. So Jim and I, if you want to advance one slide, Jim, advance it
Advance,
one
okay.
slide.
Yep.
So this is the dial indicator that Jim was talking about, and we always get asked for a part number. So I thought I was being proactive in including the part number for all of you, but Jim and I discovered like a minute before we started that is the wrong part number. So I will email you the correct part number. So as I think Jim mentioned, you don't need to buy the Hypertherm dial indicator. We strongly suggest that you buy the Hypertherm consumables, but really any dial indicator.
We're not in the dial indicator business.
We are not in the dial indicator business. It's not. So any dial indicator will do. You can walk into any store and pick up any old dial indicator. But if you have your heart set on the Hypertherm one, I will send you the part number, the correct part number. So do not try to buy using that number. You won't get very far. The other types of questions that we're getting a lot before I hand things over to Jim, we are recording this presentation, and we will make that available to you if you want to go back and review something or want other operators to listen to it. I will send you a link to watch the presentation again, probably early next week. The second thing, we will send you all of the slides that you're seeing today and even a certificate of completion. Some companies like to track training hours, so we will send that to you just so that you have proof that you have taken 1 hour of electrode training with Jim Colt. And that's it for me. So Jim, let's get to some of our questions here. You can see them. Let's see, I've answered these. So let's scroll down. Why do the 50 amp consumables have such a short life compared to the 80 amp ones?
Okay, so I'm assuming you're talking about one of our HPR XD systems or an HPR non-XD system, because they use 50 and 80 amp cut processes. In reality, the life should be essentially the same, assuming you're using each one on the thicknesses and the power levels that they're designed for. But I have run into this before. The 50 amp consumables are a little bit touchier. They have to run very close to the plate. And if you don't have pierce height and pierce delay time set properly for the 50 amp consumables, you quite often can damage the nozzle and even the electrode from 1 or 2 pierces too close to the material. So they're a little bit touchier. My guess would be take a real close look at your cutting specs and make sure that your height control is sensing the plate very accurately. In order to get proper pierce height as close as it has to be with the 50 amp consumables, you really need a function called ohmic sensing, where you can use ohmic contact to accurately sense the plate and retract to the pierce height before it fires. So that would be my guess. I mean, there certainly could be some other things wrong with the system. Our tech service guys would be more than happy to talk with you about that, or feel free to send me an email, and I'd be happy to kind of address it. It's always good like that, with a situation like that, to include pictures of the kind of wear that you're getting on the consumables, because sometimes that tells a story as far as if you're piercing too close or if there's something else going on. But they should last about the same under ideal conditions.
Yep, and I can send Jim's email and our technical service phone number. It's a toll-free number, and actual people answer the phone. I'll send that out to all of you as well so that you have that. Next question, when I cut with a 400 amp, when I cut at 400 amps on 1-inch thick metal, the hole looks rough. Any ideas what would cause that, Jim?
Well, the first thing that I think of when you get a rough hole, if you're cutting with a water table, you need to lower the water. When you use the 400 amp oxygen process on steel, water reacts with the edge of the plate. Oxygen breaks down into what it's made of. Oxygen is O2. It breaks down, and then there's a process from the plasma that produces a little bit of hydrogen, and the hydrogen pops and moves. The water, breaks down into hydrogen and oxygen, and the hydrogen from it pushes the arc around. So if you lower the water 2 or 3 inches, just enough so it doesn't splash up on the edge of the plate, that'll smooth out the roughness. Now, if you don't have a water table, then that obviously is not going to be what's causing it. That's the first thing that I always do. It scares a few people, but put your hand on the torch while it's cutting. If you have to climb up on the table, be careful. Put your hand on the torch body. You can do it back on the fiber part on the back end of the torch. If you feel any vibration while the torch is cutting, that's going to show up in the cut edge. Or could also be oscillation in the z-axis. If the height control is tuned up a little bit too tight, oftentimes it'll try to correct the height too quickly, and you'll feel a lot of up-down oscillations, very minor. They might only be moving a thousandth of an inch. That'll cause very rough edges on the cut. Once again, pictures of that kind of cut issue, forward them to our tech service guys to take a look at it, and often they can help you steer you in the right direction. The cut on 1 inch with a good smooth motion, good height control, and no water in contact with the edge should be very smooth and very shiny when everything's working right.
All right. Next question. This person has a PowerMax 65 on a
ArcLight.
ArcLight table. They have had many people tell them to keep the metal submerged when cutting, but they're concerned about doing that. Does submerging the metal impact or affect the electrode, and can it cause the electrode to short out?
Yeah, it doesn't actually cause the electrode to short out. None of our air plasma torches were designed specifically for submerged cutting. We recommend that if you do use a water table with them, that the water stays below the bottom level of the plate. If you choose to submerge it, what we run into sometimes before the actual gas flow comes on the torch gets submerged, and as soon as the ArcLight Dynamic CNC controller triggers the torch, then the gas flow starts, but already water can get up inside the torch. So the water can actually short out the components inside the torch. It doesn't cause electrode damage, but it can cause nozzle damage and can cause misfiring occasionally. So one thing that you can do, if you have a lot of parts in close rapid succession, the torch stays, the PowerMax 65 stays in post-flow. In other words, the air keeps flowing in between cuts for around 20 to 30 seconds. I don't know the exact number on that. And if it's in post-flow and you submerge it underwater, it keeps the water out of the torch, and you can do that. So, but once again, my best advice is what's in our manuals to lower the water below the bottom of the plate, not above the plate. When you look at our liquid-cooled torches, anything from our 130 amp system up to our 800 amp system, they can run 10 feet underwater if you want. They're designed for that specifically, and that's one of the advantages of high-frequency starting as well.
Okay, next question. What wears out the electrode faster? Is it piercing or cutting?
It's always a good question. So if you do a lot of piercing, you're going to get less feet of cut out of the torch. If you pierce once, you're going to get a lot more feet of cutting. So piercing wears out the electrode faster than anything else. We've actually had a few customers that didn't, they had a bunch of parts. Actually, the customer was draw tight. They manufacture trailer hitches, and they had a particular part that they had to cut thousands of a week. Didn't have any inside holes cut in it. It was just outside cutting. They switched over from piercing and cutting every single one of the parts to doing one pierce and cutting about 400 parts without ever extinguishing the torch. In fact, the torch stayed on in one case for a couple of hours. They got dramatically longer consumable life by only doing one pierce and doing it that way. So yes, piercing takes a toll on it, but something you can't avoid on a lot of parts that require internal cutouts.
Right. Why does my electrode glaze on the tip after scribing? So right there.
Why does my electrode glaze on the tip after scribing? Oh, okay. By scribing, you're talking about plasma arc writing or arc marking. I would have to know a little bit about what you're using for gases. So if you're using one of our more modern setups, HPR XD systems, you should be using nitrogen as the shield gas and argon as the marking gas. The argon makes the marking process non-aggressive, so you don't have any dross to wipe off on the top of the plate or anything like that. Normally it shouldn't do that. You should be using the right gases. You shouldn't see any glazing on it. But if you're trying to use air, or if you're using nitrogen as the marking gas, then yeah, you could have some problems with it that will affect life. One of those things I'd probably have to see to give you a little bit better advice on it. Wish I could give you a better answer.
All right. The next question, Jim, you can see that they mentioned a part number, but I think it's probably generally these two questions are the same. how do you test electrode life on an electrode that's shaped with a pointed tip or shaped like a pencil? So in this particular case, it looks like part number 220339.
Yeah, well, that's actually that's a special electrode that's used for stainless steel cutting using particular gas. No, you can't check that one. When it starts cutting bad, you've got to change that one. Unfortunately, that's the only one in our entire product line like that. So,
okay.
Good choice though. You get stumped me on that one.
Yeah, that doesn't happen very often. Next question: we seem to notice poor cut quality on our 260 amp system after getting to 0.025. What could cause this problem?
Okay, what my guess is, think about the way the torch height control works on these CNC cutting tables, is it measures the arc voltage from the attachment point where the arc attaches to the electrode to where the other end of the arc attaches to the plate while it's cutting. As the electrode pit wears, if it wears 25 thousandths, the torch gets 25 thousandths of an inch closer to the plate. There's two different types of height control setups. One of them is you just use an arc voltage setting, and an experienced operator will notice the torch getting closer to the plate, and as the electrode wears, you have to dial in a higher arc voltage to compensate. The torch wants to be at the correct physical height, and you need a higher arc voltage because the arc length gets longer because the electrode's warm. The newer technology height control systems use something called sample arc voltage. What they actually do is they pierce the plate and the torch physically moves down to the pierce height, and then when the cut starts, it samples the arc voltage. It knows it's at the correct height because you already sensed where the surface of the plate was, and it samples the voltage and automatically recalibrates the voltage on every cut. So as the electrode wears, the sampling type height control will always have the right height. The cut quality will remain consistent, but if you have an arc voltage height control, the operator needs to use his knowledge to dial in a higher voltage. So a good rule of thumb is at 25, if you've got 25 thousandths, which is a little over half worn out electrode, you should probably have to dial in somewhere between 10 and 15 volts higher in order to keep the torch at the right height. That would be my guess of what's going on.
Okay. So it's 3 o'clock, so we're pretty much out of time. I don't know if you want to look at the questions. There are a ton of questions left to answer. I don't know if you want to maybe choose one or two more to answer, Jim, from this list.
Yeah, I see one that'll be fun. So.
All right.
So somebody asked, and this gets asked quite often, what is the difference between a high definition plasma cutter and a standard plasma cutter? Standard plasma cutter, all of our PowerMax air plasma cutting systems are what you would call a conventional plasma cutter that use air. And we have two products in our oxygen plasma cutting line, the HSD 130 and the Max Pro 200. Those are industrial liquid-cooled cutting torches, but they're not high definition. So the difference between, say, a Max Pro 200 and an HPR 260, which is a high-definition system, is that the HPR 260 uses what we call a vented nozzle that has two orifices. So the nozzle orifice is designed to squeeze the plasma arc to increase its energy density. Energy density is measured in amps per square inch. That's the footprint of the arc. And so it squeezes it a first time. We relieve some pressure through the venting on the nozzle, and then the smaller second orifice squeezes the nozzle a second time, squeezes the arc a second time. That increases the energy density to about 60,000 amps per square inch. A conventional plasma torch, such as a Max Pro 200, all of our PowerMax units are somewhere in the 12,000 to 15,000 amp per square inch range. So it's better torch design. In order to make that torch work, we needed to change the output of the power supply, and we needed a much more sophisticated gas flow control that can control the gas more accurately, can ramp up the gas and ramp down the gas and current at the end and the beginning of every cut. So that's, in a nutshell, there's a lot more involved, but that's the reason that high-definition cutting gives you better, squarer, cleaner edges and a narrower cut than a conventional plasma.
Okay, we should probably stop here. But as a reminder, we will be back next week, exactly 1 week from today, talking about the other parts in a typical consumable stack-up. So, as I mentioned at the start here, nozzle, shield, swirl ring, all of that other fun stuff. And some of you, most of you, it looks like, had actually already registered for that for part 2 of this. But if you have not, there's the link again to go and register, hypertherm.com/current webinars, and then you just, of course, want to register for part 2. And that's it.
Yep. Well, thank you all for coming, and hopefully this head cold will be gone by next week, and you won't hear me hacking on this side of the room. So. Thank you much.
Thank you. Bye-bye.